Hello and welcome back to the deep dive. Today, we're digging into a topic that, let's just say, it brings back some memories from class 12.
Let me guess. Organic chemistry.
You nailed it. Specifically, we're tackling Unit 6, Haloalkanes and Haloarenes.
Ah, classic.
And our mission today is to figure out the methods of preparation. How do we actually make these compounds in a lab?
It's a great topic, and you're right. For a lot of students, this is where things can start to feel a little overwhelming. You have all these reactions, reagents, different conditions.
It just becomes a soup of information. I remember staring at my textbook thinking, why are there 10 different ways to make the same thing? It felt like just memorizing.
But there is a logic to it,
Yeah.
beautiful logic, actually. And that's our goal today, to stop the memorizing and start seeing the patterns. We're going to break it all down into 3 specific recipes.
Before we get to the recipes, I want to start with a little mystery I found in the notes. It really caught my attention.
The test tube mystery, I believe.
That's the one. So I want you, our listener, to just imagine this for a second. You're in a chemistry lab.
You can almost smell the chemicals.
Exactly. And you're holding 2 test tubes. Both have this reddish-brown liquid inside. It's bromine.
Very colorful, very reactive stuff.
Okay, so 2 tubes, reddish-brown liquid. Into the first one, test tube A, you add some hexane, just a standard alkane.
Single bonds, very stable.
And into the second one, test tube B, you pour in some butene. That's an alkene, so it has a double bond.
Right, so the key difference is single bonds versus a double bond.
Perfect. Now, you switch off the lights. It's dark. In test tube A, with the alkane phane, nothing happens. The red color just stays there. But in test tube B with the alkane, the color vanishes. Instantly, it goes completely clear.
Like magic.
But here's the real kicker. You take test tube A, the one that did nothing, and you walk it into the sunlight. And then the color fades away. So why? Why does one need the sun and the other works in the dark?
It's a fantastic question. Because that one simple observation light versus no light tells you everything. It shows that the mechanism, the actual path the reaction is taking, is completely different.
And that's the kind of detail that can make or break an exam answer, isn't it?
All the time. If you write UV light for an alkane reaction, the examiner immediately knows you've mixed up the fundamental concepts. You've mixed up the recipes.
Okay, so let's unmix them. At the simplest level, what are we doing here?
At the simplest level, we're just trying to introduce a halogen atom, like chlorine or bromine, into a hydrocarbon.
And we're starting with one of 3 things, right? Our ingredients.
Correct. Our starting materials, our pantry as you called it, has alkanes, alkenes, or alcohols. That's it.
So we're either, swapping out a hydrogen for a halogen?
Or we are adding a halogen where a double bond used to be.
Yeah.
The method change is completely based on that.
Okay, let's try to visualize this. Close your eyes for a moment. Picture a simple chain of carbons, our hydrocarbon backbone,
Minding its own business.
and we want to attach a halogen to it. The notes suggest 3 different routes, 3 different ways to attack this chain.
3 different personalities of attack, you could say.
Route 1, this one is for alkenes, and it feels violent. The notes call it kicking out a hydrogen violently.
It is violent. We call it free radical substitution. You need a lot of energy to get it started.
Which is why we need the sunlight from our mystery earlier.
Exactly. The sunlight is the trigger. It provides the energy to start the chaos.
Okay, then there's route 2 for alkenes. This one is called sneaking in through a broken bridge.
A very good image. The double bond is like a bridge that's ready to open up. You don't need to kick anyone out. The halogen just adds across it.
So no one gets evicted, it's just an addition.
Pure addition. You keep all the atoms you started with, plus the new ones.
And finally, route 3, from alcohols. This is described as politely swapping a signpost.
This is the most civilized, most precise method. You have an alcohol with its ApoH group. Think of that as a signpost. We use a reagent to just unscrew it and screw in a halogen in its place.
So we have the violent kick, the broken bridge, and the polite swap.
Chaos, addition, and precision.
Before we dig deeper, let's touch on the why we care part. Besides the board exams, is this actually important?
Oh, absolutely. This isn't just theory. Think about industry. If you want to make a specific pharmaceutical drug or even a particular type of plastic, you can't afford a messy reaction. You need a specific product.
A primary or tertiary haloalkane, for instance.
Exactly. You have to pick the right recipe to get the pure compound you need. If you don't, you waste time, you waste money, and you get a useless mixture.
Which brings us to the big misunderstanding trigger. Students think all haloalkanes are made the same way.
And that's the trap. The choice of method depends completely on your starting material and on the regiochemistry.
Regiochemistry, that sounds complicated.
It just means the geography of the reaction. Where on the molecule does the halogen end up? The beginning. The middle. The method decides that.
Okay, that makes sense. Let's use the main analogy from the notes. The 3 routes to a destination.
Perfect.
Route 1, the free radical one for alkanes, is the long road. Imagine the alkane is a very stable, happy car. It doesn't want to react.
Very inert. Chemically quite boring, actually.
So to get it to do anything, you need a spark. That's the UV light. The UV light hits a halogen molecule.
And splits it into 2 halogen radicals.
And a radical is what, in simple terms?
It's an atom with an unpaired electron. It's extremely unstable and aggressive. It will attack anything to find a partner for its electron.
So the halogen radical is like a speeding motorcycle that just crashes into the stable car to knock a passenger hydrogen out.
It's a chain reaction, a total crash scene. And like any crash, it's very, very messy.
What do you mean by messy?
I mean, it's non-selective. That aggressive radical doesn't care which hydrogen it hits. It might hit one on the first carbon or the second or the third. You end up with a mixture of all possible products.
A mixture of isomers. So if an exam question asks for one specific product...
This is almost always the wrong method to choose. Separating that mixture is a nightmare in the lab.
Got it. So, messy crash, bad for purity. Now, route 2, the detour via bridge for alkanes.
Yes, addition. This one is so much cleaner.
We saw in the test tube, right? It was instant. No light needed. Why is it so eager?
It's that double bond. It's packed with electrons, so we say it's electron-rich.
So it's like bait for the halogen.
Exactly. The halogen molecule is attracted to that electron density, the double bond breaks open, and the halogen atoms just snap onto the 2 carbons.
And it's predictable.
100% predictable. They will attach only to the carbons that were part of the double bond. It's regioselective. No messy mixture.
That sounds much more useful for industry.
It is. Take PVC pipes, the white pipes you see for plumbing all over India. Polyvinyl chloride.
Of course.
To make that, you need vinyl chloride. Industry makes it on a massive scale using addition reactions. They can't afford the messy free radical method. They need a process that is clean, selective, and scalable.
Okay, that makes sense. Now for the last one, route 3, the direct road. Substitution from alcohols.
The polite swap. This is probably the most common and controlled method you'll use for synthesis in the school lab.
And why is that?
Because alcohols are readily available, and the reagents we use, like PCl3 or SOCl2, are designed to be very specific.
So they're like special tools?
They are. They are designed to attack only the carbon-oxygen bond of the OH group. They don't touch any of the other CH bonds in the molecule. They just zoom in, pluck out the OH, and place the halogen there.
So it's like surgical precision. If I have a really complex molecule, I can change just that one little spot.
Exactly. You preserve the rest of the molecule structure. That's why we call it nucleophilic substitution. It's a clean, controlled swap.
The notes mention this became popular in the 1940s and 50s.
Yes, because as chemistry got more advanced, the need for purity became critical. The old radical methods were too messy for making complex molecules like medicines. This method using alcohols was a huge step forward.
Let's try to lock this in with a mental movie. Picture a lab bench with 3 workstations.
I like this.
Workstation 1 is just chaos. Flashing UV lights, sounds of crashing, halogen radicals are bouncing everywhere, hitting an alkane molecule randomly. It is a complete free-for-all.
That's our free radical substitution. High energy, low control.
Now move to Workstation 2. It's quiet here, smooth. You see a halogen molecule just glide towards an alkene. As it gets close, the double bond opens and snap. It locks perfectly into place.
A smooth converging motion. That's addition. Spontaneous and predictable.
Finally, Workstation 3. This looks like a high-tech clean room. A robotic arm, which is our reagent, moves with precision. It approaches an alcohol molecule, carefully plucks off the OH group, and clicks a chlorine atom into that exact same spot.
Pluck and place. Surgical. That's our nucleophilic substitution.
Chaos, snap, and pluck. If you can remember those 3 images, you've pretty much got the core idea.
That's a great way to summarize it.
Okay, but we need to get ready for the exam paper. Let's run through these exam-safe clarity lines, the golden rules.
Let's do it. These are the key takeaways.
Rule number 1. Free radical substitution of alkenes requires UV light or heat.
This is so important. If you write the reaction happening in the dark, it's 0 marks. You must write UV or heat on the arrow. No energy, no radicals, no reaction. Simple as that.
Right. Rule number 2. Addition to alkenes occurs spontaneously at room temperature without UV light.
And the trap here is just putting UV light on everything out of habit. Don't do it. Alkanes are naturally reactive because of the double bond.
Yeah.
They don't need the extra push.
Got it. Rule number 3. Free radical substitution is non-selective. Addition and alcohol substitution are selective.
So if an exam question asks for a specific isomer, say 2-bromopropane, do not use the free radical method. You'll get a mixture of 1-bromo and 2-bromo, and you'll lose marks for choosing a poor synthetic route.
Okay. Rule number 4. When reacting with alcohols using reagents like PCl3 or SOCl2, only the OH group is replaced.
This is a lifesaver in complete the reaction questions. They might give you a huge, scary-looking molecule. Don't panic. Just find the OH, swap it for the halogen, and copy the rest of the molecule exactly as it is.
And the final most important rule, method choice depends on the starting material.
This should be your first thought. When you see a question, ask yourselves, what am I starting with? An alkene. An alkene?
Yeah.
Or an alcohol. That single question tells you which of the 3 paths you have to take.
So to wrap up this entire deep dive, let's do a quick revision. Core idea. We make haloalkanes from 3 things. Alkanes, using substitution. Alkenes using addition. Or alcohols, using substitution again.
Remember the mental image. The 3 workstations. The messy radical chaos. The smooth snap of addition. And the precise pluck in place with alcohols.
And the key example to remember is PVC pipe. Industry needs precision, so they use the addition method, not the messy radical one.
And for the exam, remember the clarity lines. Light for radicals, no light for addition, and specific reagents for alcohols.
Once you know the starting material, you know the method. It's a clear choice.
Keep practicing these recipes. It really is that logical. You've got this.
That's all for this deep dive. Thanks for listening. We'll catch you in the next one.